Hello, everyone. Welcome to lecture 30 of AREC's risk rate. Today, we will continue with risk and production. So there will be two parts of the stuff that I want to cover today. First is I want to introduce the concepts of certainty equivalent and risk premium. And to tell the certainty equivalent level and the risk premium levels, we first need to know whether the person is risk preferring, risk averse, or risk neutral. And I will also get to that because depending on the person's risk aversion level, then the CE, certainty equivalent, and risk premium might be different. And after that, we will use an example to illustrate how you can do the EV analysis, or this time I will call this the quadratic risk programming. We had linear programming before, but this time we will do a little bit of extension, so the objective function is no longer linear. All the constraints are still linear, so that's the type of the quadratic risk programming. And we will get there, use an example. And the readings still, I would recommend that you read both Hadakar et al. Chapter 5, Chapter 7, and then for the quadratic programming analysis, then Kim et al. 2018, the Chapter 8 and 9 are good for that. We can tell whether a person is risk neutral, risk averse, and risk preferring by the relationship of the utility of expected profit and the expected utility. So if the person is risk neutral, that means that person is indifferent between a safe and a risky outcome. So here, think of the risky outcome of what we have shown in this table here. This without insurance is a risky outcome. So half chance is 16,000, half chance 4,000. However, a safe outcome is here is with insurance. So those are the safe outcomes. So a risk neutral person is actually a difference between safe and risky outcome. That means that person's utility curve is a straight line. Then here, this is the expected profit. The utility of the expected profit is here. So this utility of the expected profit, it should be on the utility curve, or here it's a utility line. And you also want to know the expected utility here. So the expected utility is where you find those 2 points and you draw a straight line. And because here the outcome are, the probability of the 2 outcomes are half and half. So along that straight line connecting those 2 utility, and in the middle point, that is the utility of expected, that is the expected utility. And when the utility curve is a straight line, then those 2 points, they are the same. And that's actually have it here. Let's actually here take a look at the risk averse person's utility curve. So here, this is what I started introducing the concept of utility of expected profit and expected utility. So if the utility curve is having this shape, then this person is risk averse. The reason is because the utility of expected profit here, so the blue dot there, is greater than the expected utility. So this one, it is the utility the producer got from the safe outcome. And on this side, the red point there is the expected utility of the risky outcome. So if the person prefers, or if the person prefers the safe outcome over the risky outcome, then the person is risk averse, and that's the preference. And if we use the utility function to do that, that means this utility here of the safe outcome is greater than the expected utility from the risky outcome. So if that's the case, then that person is risk averse. And here, if a person's utility curve is having this shape, and this is a shape for a concave function, and here for the risk averse person, this is actually a convex function. So anyway, here, if the utility function is having this shape, then that means this person actually is getting a higher expected utility from the risky outcome. And the utility that person can get from the risky outcome is actually higher than the safe outcome. So if that's the case, then that person is apparently a risk preferring or risk seeking person. So you can think of this as somebody who would go to casino to do gambling, and that will be the shape of the person, the shape of those kind of person's utility curve. So that's how you can tell whether a person is risk neutral, risk averse, or risk preferring. So basically, that's decided by the shape of the utility curve that person is having. And once we get that, then I will introduce the concept of certainty equivalent and risk premium. So I will use here, as you can tell from the graph here, use the risk averse person's utility curve as an example to introduce what's CE, because as I mentioned before in this course, most of the time the producer is risk averse, and also in reality, most person under most circumstances, they are risk averse. So risk equivalence, or here I call it pi CE. CE is for certainty equivalent. So this is the level of profit, as you can tell that I use the letter pi, which is the letter we have been using in this course to denote profit. So CE is a level of profit. It is the level of the profit that will give a person or the producer or the farmer the same level of utility. So pay attention here, that will give you the level of utility as the expected utility of profit. So expected utility of profit is this term. We have the E, which is the expectation operator outside. So expected utility of profit. So that's how you read that. And to find out the CE, you first need to find out the expected utility of profit. So here, since we're finding the expectation of something, we first need to find out the utility of profit under the two different outcomes. One is good weather, the other is bad weather. So let's forget about this expectation operator here. However, find out the two utility levels first. So under bad weather, that's the profit. And utility, remember, utility of that profit, you have to go to the utility curve. It's here. And good weather, this is a profit, and this is the utility of that profit. So we find out the utility of the profit under good weather and bad weather. If we want to find out the expected utility, then we draw a line, a straight line connecting those 2 points. And here again, because the probability of good weather and bad weather happen is the same. So once you connect those 2 points and in the middle of that segment, which is here, so this point, as you can tell, that point is the point where the producer or the decision maker, that's the level of the expected utility. So again, those 2 points are the utility of profit under good weather and under bad weather. And this red point here is the expected utility. And again, you can see from here, because the utility curve is not linear, it's nonlinear. So this expected utility is not on the utility curve. I hope you'll be super clear about this. So the CE is where this expected utility, if you go horizontally to the utility curve, there's a point here, that's green point. So the red point and the green point, those 2 points have the same level of utility. And this green point here, it is associated with a profit, a level of profit. And that is exactly the certainty equivalent that we're looking for. So again, if you read the definition here, it is the level of profit. So this profit, 8,000, this profit where the utility of that profit or utility of CE, whenever we say utility of something, it's on the utility curve. So this utility of CE is on the utility curve. So that utility is the same as the utility, as the expected utility. So expected utility, unless it's a linear line or the person is risk neutral, then if the person is either risk averse or risk preferring, usually that's not on the utility curve. However, the green point and the red points here, they are having the same level of utility. So that's how you find the CE. You first, step 1, you find the utility under different outcomes. So in our example, it's good weather, bad weather. You find the 2 utilities there and you calculate the expected utility. So because here the probability of good weather and bad weather happening are the same. So the way that you find the expected utility is just draw a segment between those 2 utilities and find the midpoints. That's your expected utility. And step 3 is once you find that red point there, then you go horizontally to the utility curve and you find this green point here, and then you go down to the horizontal axis and find out the profit level there. So CE is a level of profit. And once you find your certainty equivalence here, and in this example, it is 8,000. If you still remember from last lecture, we have a table here of different preference over different outcomes, and you can see here that 8,000 is the level where the decision maker is indifferent between taking the risk or get a certainty equivalent. So this is a certainty equivalent. So that's how you link that certainty equivalent with the with that table of the preference. So once you know what is certainty equivalent, then we can calculate the risk premium. And risk premium here, I have the mathematical equation here, is the expected profit minus your certainty equivalent. So this is the profit under bad weather, the profit under good weather. Expected profit is here, 10,000, and certainty equivalent we have explained is 8,000. And the difference between those two are the risk premium. So it is the maximum that the decision maker would pay in dollar value to take the risk away. So usually if you're a risk averse person, then the risk premium will be positive. So you would always prefer to have a certain level of payment than here taking the risk, and then half of the chance is 4,000, half of the chance is 16,000. So that's risk premium. And here I have a summary of the risk premium and risk preference. And you can tell here there are 3 different types of utility curves here. And this convex curve here is the risk averse person. This concave curve here is the risk seeking or risk preferring person, and that straight line means that person is risk neutral. And your the risk RP here is for risk premium, and you can see it's the same. It's the expected profit minus the certainty equivalent level of profit. So if it's greater than 0, risk premium is greater than 0, that person is risk averse. And if it's equal to 0, means that person is risk neutral, and smaller than 0, it's risk seeking. So I have shown you how to find the certainty equivalent and the risk premium for a risk averse person. You should go back here for this risk seeking or risk preferring person. You should try yourself on this graph to find the certainty equivalent level. So I'm gonna show you very quickly here. And if you're not following, you probably should pause and think in a little bit more time about this. So first, you find these 2 utilities, and then you find the expected utility, which is still the red point here. And then you go horizontally to the utility curve, and that is that point. So that point is having the same utility as the expected utility. And then you go down here, that will be your pi CE. That's your certainty equivalent. As you can tell from here that for a risk preferring or risk seeking person, pi CE is greater than the expected profit here. Okay, so a little bit more explanation about certainty equivalent. So again, that's the amount, the certainty amount. This is similar like if the producer or the farmer buy insurance. Once you buy insurance, no matter good weather or bad weather, you will always get a certain certainty payment. So that's the certain amount that makes the decision maker indifferent between taking the risk or taking the certain payment. So if in this table, the person is indifferent, or the farmer is indifferent from taking the risk, which is this side, or take the certain amount is under the insurance. So that is when that person is indifferent, then that's the amount of the CE that you're looking for. So in reality, in order to find a certainty, a person's CE level, you probably need to interview the person and then ask a bunch of different levels of those numbers and say which level of profit makes the person indifferent between taking the risk and taking the certain payment. And here in this table, it is one decision maker's preference. Another producer or decision maker might have a different preference. Again, for example, there might be a person who's indifferent at the level of 7,500, and that will be that person's CE level. So different person might have different CE levels. And the risk premium, again, it is the difference between the expected profit and the decision maker's CE. So it can be sort of the cost to the decision maker to have to bear the risk of an uncertain outcome. And that's similar to the risk premium when you buy a car insurance. So there are some properties of CE and risk premium. So again, first is I've mentioned to you that different person might have different CE, even for the same level of risk. So everyone might have a different risk preference. And when the person is choosing between two risky outcomes, then usually the person should choose the one with a higher CE. So that's a decision criteria. And for a particular decision maker, the CE is lower when the risk is higher, or when they, because we mentioned that before that we can use variance or standard deviation to measure risk. So when you're having a higher variance or larger variance, then the risk is higher. And that if that's the case, then the CE is actually lower. So here I have an example of, we had canola and wheat. Imagine that we have a third crop here, which is potato. So potato, it's again half and half chance. However, they profit under good weather is larger than the profit of canola under good weather, and the profit under bad weather is less than that of canola. So here potato is having a larger variance or larger standard deviation. You can verify this. Try to calculate the variance or the standard deviation for potato. Use the equation, the formula we introduced in last lecture. So again, if you do that, you should be able to find that potato is riskier than canola. So it is less attractive than canola, which is offering 16,000 or 16,000 and 4,000 under different weathers. So that's the CE and risk premium. And once we understand that, then we can use the expected utility theory to do some analysis. So in reality, the direct estimation of a decision maker's utility function is usually not very successful for many reasons. Here I listed 3 reasons. First is that the decision maker might lack familiarity dealing with probabilities. So imagine that you're interviewing a producer, a farmer, and you're trying to interview the person asking, for example, if you're having this 10% of the chance or 10% of the probability of something happening. And for a very simple case, it might be okay, for example, half and half chance. Once the situation becomes a little bit more complicated, then because the decision maker might not be familiar with probabilities, then the results you got from that interview or the survey, then it might not be credible. And even when you're when the decision maker is having good understanding of probability. Sometimes when you're interviewing different producers, there might be differences in the interview procedures. Sometimes, depending on how you frame one question, you might get different answers. And if that's the case, then for example, the profit that you solicited from the producer, that might be different. So that is purely due to the difference in the interview process. And another most important factor here is because here when we're interviewing the producer, you are kind of asking a subjective probabilities, and it might depend on that person's mood when you're interviewing that person. Sometimes it might be higher, sometimes it might be lower, the probability, the subjective probability. So it is again not very credible, and it's because of those reasons then the direct estimation of the utility function has not been successful. And does that mean that what I have just shown you using the expected utility to analyze risk is not valid, is not useful at all? And the answer is no. And we have the expected utility theory there, and even we cannot directly estimate the utility function, we can take a alternative approach. So instead of directly estimate the utility function, for example, this could be similar to the production function we have learned in this course. You might assume it's a Cobb-Douglas utility function, or you might assume it's a linear utility function, or maybe other forms. However, if directly estimating that function form is not successful, then an alternative here is try to approximate the utility as a function of the moments of the probability distribution. If you still remember what you learned from statistics, or maybe they didn't introduce this concept here, but generally the mean is the first moment and the variance is the second moment, and there's the third and the fourth moment depending on the distribution that you choose. So here, once we do that, the concern here is the probability distribution rather than the utility function form. So if that's the case, then we might still be able to use the expected utility theory, and we can avoid directly estimating the utility function. So I do have an example here, and this is called the E-V analysis. And again, E is for expectation and V is for variance. And for this analysis, it is linked to the linear programming method that we have learned in previous lectures. However, here, the objective function is a little bit different. So the objective function here is expectation minus phi times V. So this V is the variance, and as we mentioned that variance is a measure of risk. So if that portfolio is having higher risk, then the utility you get from that portfolio is lower. So for example, here, if canola is having higher risk, then the utility you got from canola is lower. If compared to wheat, they're having the same level of expected profit. However, canola having a higher V or higher risk, then for the producer, it will get penalized in the utility function. So this quadratic programming problem is maximize this utility, which we define as E minus phi times V, and subject to some constraints. It's similar to the constraints we have seen in the linear programming section. For example, there could be land, labor, and so on. So we can here assume that there's a farm that is having multiple activities here. So what are the multiple activities? You can think back to the beginning of the linear programming problem. The activities are growing tomato and potato, or you can link back to the wheat and canola example. And those are the activities here. And how do you exactly get this E and V and also this phi here? We will use an example to illustrate how you get those, but let me have a brief introduction of those terms here. It could be a little bit abstract, so it's okay if you don't understand it now. But later on, after you see an example, you can probably come back to this slide, and I think it will help you understand this concept. So the E here, as I mentioned, is the expectation or the mean, and here it is the summation of EI times XI. So XI is the level of the ICE activity, and EI is the expected profit of the ICE activity. And it's okay if you don't get it now, but later on we can come back to here. And V here, it is the covariance. Sorry, we're having a new concept here. And I did provide a formula here, but in this course, I'm not expecting you to calculate the covariance. Rather, I will just give you a table of covariance. So don't worry about this mathematical expression here. It is trying to give you the formula, and if you're interested, you can probably take another course, statistics course, or maybe econometrics course, and if that's what you're interested. But don't worry about it. I'm not asking you to calculate that in this course. So it's the covariance between the ICE and the JCE activity. And when your I and J are the same, then that become the variance that I have introduced in the last lecture. And the phi here is the decision maker's risk aversion level. Let's look at the term that's the easiest in the objective function, and that's phi here. So phi is the decision maker's risk aversion level, and usually we can use different numbers to denote the different levels of risk aversion. For example, if phi is 0 here, and this objective function just simplified to E. So the person only cares about the expected profit, and there's no penalty for risk, which is measured by this V here. So no matter how big the risk it is, the person only cares about E. And if that's the case, then we say that person is risk neutral. And there are several other levels here, and usually if that phi is equal to 1, then we say the person is somewhat risk averse, and we say that person is having a normal level of risk aversion. And then in between 0.5, it's hardly risk averse at all. It's a little bit. But there are some other levels. There are 2, 3, 4. 4 is extremely risk averse, and there are different measures of risk aversion in the literature of economics. And if you're interested, you can probably dig more into that. And here I just introduced to you a very simple or more easy way of to understand the risk aversion level and to move on our EV analysis. But when you're actually doing research and trying to measure a person's risk aversion level, it is not as easy as what I'm showing you here. You just assign a number to that person. So let's use an example to illustrate this EV analysis. So here we're assuming the farmer is growing 3 crops, corn, wheat, and soybean. And this time we are assuming that there's a 3 months lag between planting and harvest for all 3 of these crops. And there's uncertainty here is due to this lag between planting and harvesting. So when planting, the farmer need to decide how much land to allocate to those 3 crops. However, at the time of planting, the farmer doesn't know with certainty the per unit profit of each crop. And however, the farmer have some knowledge of the profit of those crops in the past. So the farmer is expecting that the unit profit of each crop will be equal to the mean profit over the last 10 years or last 10 periods. So assume the farmer collected information about the profit of the 3 crops in the last 10 years and put all of the information in this table. So this column here is telling which period it is. So there's 10 periods here. And for each crop, there's an associated profit for each period. So those are information in the past. So that's what the farmer observed. And for the current year, the farmer doesn't know for sure what the profit will be. So instead, it just assumes that the profit is the average or the mean of the profit for the 10 years in the past. So here, again, we're assuming the farmer is allocating the same probability for each of those 10 periods. So the probability for each year is 1/10. And using that probability and the profit for each year, the farmer then calculated the mean, or here it is the simple average here. And given that profit, then the farmer also have some constraints. So this is again very similar to the constraints we have observed, learned in the linear programming problems. So there's a hired labor constraint, there's the family labor constraint, and there's machine time and land. So there's 4 different constraints here. I just put them in a table. You can, when you're formulating the mathematical expression of this problem, you can use this information here. So those are the technical coefficients, and those are the right-hand side values, and there's units associated with each of those constraints. And let's remember, for the objective function, there's 3 components there. We talked about phi, and let's work on E the next and leave V to the last. I consider that to be the most difficult term in this objective function. So again, here E is the summation of the profit that the producer can get from each activity. So first, what is this Xi here? This is the level of the i's activity. So here, in this example, we have 3 activities, and we have to decide how much land to allocate to each of the 3 activities: growing soybean, growing wheat, and growing corn. And I use just the first letter of the 3 crops to denote the level of the activity. So S here is the acres of land allocated to growing soybean, and same with wheat and corn. So W here is the acres of land allocated to wheat. And this EI here is the expected profit for the i's activity. And this information is available in the table here. So E soybean is 91, and E wheat is 110.7. And there's also profit for corn. So now, with the information we have, we can write the objective function in a little bit more explicitly. And here, this 91 is the EI for soybean, and that is the unit price for soybean. So that, sorry, not the unit profit. It's the profit the producer, or the expected profit. The expected profit the producer can get from growing 1 acre of soybean. And then 91 is a unit profit times the level, the acres of land allocated to soybean. Together, that's the profit that the producer gets from growing soybean. And again, you get the profit for wheat and the profit for corn. So we get the E part of this problem solved. Then we need to figure out this V here. We already talked about phi, and after we talk about V, we will put everything together. So in order to know how to express V, we need to get a little bit, get to know a little bit better about variance and covariance. So we have introduced E, we have introduced V, and this one, the covariance between X and Y, that's the new term here. It is also an expectation. So it is an expectation of X minus its expectation times Y minus the expectation of Y. Again, I'm not expecting you to be able to calculate it, but from this expression, there's something that you can learn about covariance. So I do hope you understand what covariance is mirroring, and this expression here can help you understand that. So it is a measure of how X will vary with Y. So you can think of X as growing corn and Y as growing wheat. And if we assume X and Y are independent, this covariance is equal to 0. So if those are independent, then they do not influence each other. But usually most of the time, covariance is not equal to 0. So when it is positive, that means, so here, this value is greater than 0. So that means that high values of Y tend to associate it with high values of X. So if you pay attention here, then if covariance is greater than 0, that means they tend to move together in the same direction. So if the profit for wheat is higher, that means the profit for corn is also higher. However, if the covariance is smaller than 0, then high values of X will be associated with low values of Y. So they're moving in the opposite direction, X and Y. Let's look at the example to help you better understand this covariance. So again, here we're looking at this V, and again, V here is not just variance. It's a variance covariance table, and when I and J are equal to each other, then it's variance. If they're not equal, then it's covariance. So for example, this is in this table, let's say soybean is 1, wheat is 2, corn is 3. So here is 1, 1. It's both soybean. And here it's both wheat. So this is 2, 2, this is 3, 3. So those three terms are the variances. And for the other terms here, that negative 65, the I's activity is soybean, however, the J's activity is wheat, so they're not equal to each other, and that's the covariance term. And that's actually let's focus on the variance first and leave covariance for a little bit later on. So here, if you compare these three variants, you can see that corn is associated with the largest number here. And we mentioned that variance is a measure of risk. The higher the variance and the higher of the standard deviation, then the higher of the risk. So you can tell from here that corn is having the highest risk and soybean here is having the lowest risk. And let's also take a look at the covariance here. So we can see here, wheat and corn is having a positive covariance. So that means the profit of wheat and corn move in the same direction. So if profit of wheat will be higher due to some circumstances, then the profit of corn will also be higher. So those two profits move in the same direction. That's why it is having the having a positive covariance. And I forgot to mention here, in this table, you only see half of this table and the other half is blank. That is because it's symmetric. So here it will be negative 65. So the covariance between soybean and wheat is the same as the covariance between wheat and soybean. So it will be exactly the same. So that's why I'm only showing you half of this table. For example, this number here will be corn, wheat will be positive, sorry. So it will be 142.2. And this corn and soybean will equal to soybean and corn. So -7, this is 65. So that's a full table, but usually it's enough to show half of the table. And we also have the negative covariance here. So it's between wheat and soybean. That means that the profits of those two crops move in the opposite direction. If the profit of wheat increase, then the profit of soybean decreases. So that's what that covariance is meaning. So then we are ready for this V term here in this EV analysis and also in your objective function. So this is our E. We worked on that already. And this V, again, as I mentioned, is a variance covariance table. So this V is, pay attention here, it has two components. So it is, if you remember, it's the I and J and of that V and Vij term. So that Vij term will be each of those terms here. And for let's first work on the three on the diagonal of this table. Those are the three variances there. So it will equal to that 32.6. That's a variance for soybean times S squared. So it's because it's S here, it's also S there. So that's S squared, and same for wheat and for corn. For the covariance here, you have to pay attention. It has a 2 there. It's because that's focused on the wheat and soybean. So we have one minus negative 65 there, and we also have another here. So that term here is actually minus 65 times SW. And then you also have a WS, so you have to minus here, minus 65. And then since we have SW and WS, then we can simply add a coefficient 2 there. So for variances, you don't have that 2. However, for covariances, you do have that 2 there because it appeared twice in your covariance table. So same for SC and WC. And again, here, those W, S, and C are the levels of the activity. Is the acres allocated to S for soybean, W for wheat, and C for corn. So that's how you formulate the E component of your objective function. I think I made a mistake here about the sign. Let me do this again. So this V is actually, it's a summation of Vig, and this is sum over I and J. So the reason we're having this negative sign there is because we're having a negative here. So it is actually those variances terms, the three variance terms plus negative 65 times WS, and then plus negative 65 times SW. And then if you simplify that, that becomes minus 2 times 65 WS. So that's how you get that negative sign there. And for wheat and corn, because the covariance is a positive term, then you ended up with a positive there as well. So we figured out this V here, and now it's time to put everything together. So again, remember those are the constraints that we have mentioned before. I give you guys this table. Then since we have already defined the 3 activities or the 3 decision variables here as W and C, then you can convert this table into the mathematical expressions of those constraints. And if you combine the objective function with the constraints, then we have the full quadratic programming problem here. This is the objective function. And if you spell every term out, then that's your objective function. And pay attention, there's a -5 times that everything else in the bracket here is the V term. And then you subject to 4 constraints here. So I will stop here today, and next lecture, we will continue with this example. I will show you how you do this in Excel and how can you do some risk analysis.